Section 3.1 is on page 168. It talks about an increasing and decreasing function. This is going to be very important to us because we need to know when is the profit increasing, when is the profit decreasing, when is the cost increasing, when is the cost decreasing, and when does the revenue increase, and for what values of product X does the revenue decrease. So first we need to talk about mathematical concept. Use the graph to determine where the function is increasing and where is it decreasing. The way we're going to do this, we read a graph left to right. The equation, we're going to do that algebraically in a minute. For now, we're going to look at this, and do we notice that here, if I'm walking left to right, you're increasing right there? So we're going to say f is increasing. That's the notation for increasing. It seems from negative infinity to x equal negative 2. Then what happens? After that, say you are at the top, you start coming down. That means f is decreasing all the way to this point. And we say f is decreasing from negative 2, always in terms of x, to 2. And then after that, do you see that we start increasing again? So if we have more than one interval, we use union. Give it some space. Union with 2. And this seems to be increasing all the way to infinity. And that would be my answer. If I look at number 4, well, it's the same kind of idea. If I read this graph left to right, I want to know where is f increasing and where is f decreasing. Well, left to right, it seems I'm going up from negative infinity all the way to this point. Do you see that this is a negative 6, negative 9? So this is negative. They're moving in threes along the x and the y in this case. So f is increasing from negative infinity to negative 3. Then what happened after that? Then it decreases to this point. Then f decreases from negative 3 to this point. This point is 0. Then it increases again. Again, left to right. Always left to right, no exception. So it's increasing also from 0 to 3. And then after that, do we agree that you start coming down, which means you're decreasing from 3 all the way to infinity. So again, to be able to tell on a graph where does f increase or decrease, you read the graph from left to right. Now we're going to do this by hand. And to do that, we're going to use a very nice trick. Test for increasing and decreasing. This is what somebody figured out along the way. If you take a derivative and you take some points a and b, if the derivative is negative, then the function itself is decreasing. That's what this is saying. If the derivative is negative, the function is decreasing. We're going to show that by a straight line coming down. That's going to help us a lot. Left to right, that's decreasing. And if the derivative is positive, so you pick a test point and you check. If the derivative is positive, the function is increasing. And this doesn't change. And if the derivative is 0, then we say f is constant. And we're going to use this analogy all throughout. That's going to help us a lot. And I'm going to start with number 6. Did I give you a page number? Yeah, page 176. So if I look at this problem and I want to figure out algebraically, we're not going to graph this. We're going to do this by hand. This is y. I want to know, forget this. I'll get to this in a minute. If I want to know where this function is increasing and decreasing, I'll take a derivative. Isn't the derivative 4x cubed? Now, I need to know where that equals 0 because I need the break point. Where does x cubed equal 0? That's when x equals 0. So 0 is really the neutral point. There's the derivative, and there's y. I pick a test point to the left of 0, let's say negative 1. and I plug it in my derivative, which is right there. If I put a negative 1 there, 4 times negative 1 is negative. I don't care about the number. I just care about if it's plus or minus. And if it's negative, I know that the function is decreasing. And I pick a point in that region, any point, say 1. If I put a 1 right there, 4 times 1 is 4, that's positive. And if the derivative is positive, that means the function is increasing. So I've just shown algebraically, and this is how we're going to show, f is decreasing right there. That is from negative infinity to 0. And we've just shown that f is increasing from this point to infinity. And that kind of matches what they're doing. We don't care much about that. So it says show. We don't need the show. That's how we're going to show every problem. So here we go. One more thing that we need. Critical numbers. Critical numbers, if f is defined at a point C, then C is a critical number if the derivative equals 0 or the derivative is undefined. And critical numbers pretty much are those values right there. Now if I told you I'm moving way ahead, if I told you this point, if I was coming down and going up, is that a maximum or a minimum? Again, this is extra. Do you notice this is a minimum? Y has a minimum at x equals 0. And that's very important because I'm trying to minimize cost and maximize profit or revenue. So to find the critical numbers, for number 10, I'll take a derivative. That is 28 minus 4x. I'll set that equal to 0. And it's defined everywhere, so this doesn't work. And wouldn't that be negative 4x equal negative 28? And x will be a 7. So x equals 7 is the critical number. Critical numbers are pretty much where they break off between positive and negative most of the time. So they're numbers that are very important. Sometimes it's not negative and positive, but you need to find those anyways. For number 12, you take a derivative, that's 4x cubed minus 16x. You set that equal to 0, and that's where the factoring comes in. If you remember, we factored, and I said we're going to need that later on, and this is where your factoring comes in very useful. This is equals 0 at 0, this equals 0 at 2, and this equals 0 at negative 2. Those would be my critical numbers. So this is defined everywhere. But if I look at number 14, if I take a derivative, I need to use the quotient rule. So if I take a derivative of the top times the bottom, minus the top times derivative of the denominator, all over the denominator squared. Now I need to clean this up because I need to know where does this equal 0 and where is it undefined. That's x squared plus 16 minus 2x squared divided by x squared plus 16 squared. This derivative would be 16 minus x squared over x squared plus 16 squared. So, where does the derivative equal 0? And where does the derivative undefined does not exist? Well, a fraction equals 0 if the top equals 0. That's when x equal a 4 or a negative 4. And a fraction equals 0, it does not exist, or undefined if the denominator equals 0. But that could never happen. So I only get 2 critical numbers out of that. And now, what's the importance of critical numbers? This is where I'm going to put on a number line and test to its left and to its right. And this is now putting the whole thing together. If I want to figure out where a function is increasing, decreasing, I need to find the critical numbers first. Find the critical numbers, and where's the function increase, where's decrease, always open interval. Use a graphing utility. We're not going to worry about that. Do not allow a graphing calculator. So I have 5 of these problems. To figure out where a function is increasing, decreasing, I need to figure out the critical numbers, so I need to take a derivative. And I need to set that derivative. Where does it equal 0? Where is it undefined? Here it's defined everywhere, but it equals 0 when x equal 2. So 2 is the only point that I need to worry about. And I'm going to do my testing. I'm going to take a derivative and make my conclusion about y. I pick a point at the left of 2, let's say 0. If I put 0 right there, would that be positive or negative? The derivative will be positive 8. All what you care about if it's positive. And if you pick a point to the right of 2, let's say 3, negative 12 plus 4 plus 8 is negative. So, we agreed positive increasing, negative decreasing. So you say f is increasing from negative infinity to 2, and f is decreasing from 2 to infinity. And that's pretty much all you need. The critical numbers are very useful in figuring out where the function increase and where the function decrease. So factoring, radicals, whatever we learned in the A sections, A3, A4, A5 are going to come in handy. The same deal with number 22. If I take a derivative, that's 3x squared minus 3. Where does that equal 0? Factor a 3 out. So the critical numbers are x equal 1 and negative 1. That's where I'm going to do my testing. Negative 1 and 1. That's where the derivative equals 0. The function is constant. So if this is the derivative, this is f. Well, let's see. Pick a point to the left of negative 1. Let's say negative 2. If I put a negative 2 here, here, or here, negative 2 in there, that's 4. Times 3, that's 12. 12 minus 3 is positive. If I pick a point between negative 1 and 1, let's say 0. Put a 0 there. 0 minus 3 is negative. And let's say 2. 2 squared is 4 times 3. 12 minus 3 is positive. So positive going up, negative coming down, positive going up. And now I can conclude what? I can conclude that f is increasing from negative infinity to negative 1, union with 1 to infinity, and f is decreasing only right there from negative 1 to positive 1. And this is very important. 32 is a bit of a mess, just a bit though. And how is that? I'm going to write this as 9 minus x squared to the 1/2. I take a derivative, bring the power down, subtract 1 from the power, times the derivative of the inside. The 2's cancel out. The derivative is negative x divided by the square root of 9 minus x squared. Now, where would my derivative equal 0? A fraction equals 0 if the top equals 0. Where would my derivative not exist? My derivative will not exist if the denominator equals 0. That's when 3 minus x into 3 plus x equals 0. X equals 3 and negative 3. So, on a number line, I'm going to put in a negative 3, a 0, and a 3. There's the derivative and there's f. Now, keep in mind, this is the upper half of a circle. So the domain, you can be to the left of -3 or to the right of +3, because if you put -4 in there, that's going to be 9 minus 16, which is negative undefined. So remember, everything works as long as the function is defined. So I need to pick only in those regions. If I pick -1 and I put that in my derivative, and my derivative is right there, that will be a minus a negative is a positive. If I put a 1 in there, square root of 8 is positive. Positive over a positive is a positive. The function is increasing. If I pick a point in there, let's say 2, minus 2 is negative, and 9 minus 4 is positive. Negative over a positive is a negative. So from this I know that f is increasing from -3 to 0, and f is decreasing from 0 to 3. And that's pretty much what we're going to do. Algebra, there's only one application problem that I have for you, and I picked all the different combinations that you can come across. Some of those are messier to play with algebraically than others. And let's tackle number 38 and 40. Those are the last problems we have. So if I take a derivative of this, derivative of the top times the bottom, minus the top times derivative of the bottom, all over the bottom squared. And I need to clean this up because I need to know where this equals 0, where is it undefined. It would be best to factor a 2x out of that. I'll be left with an x squared plus 4 minus x squared. You could do this any way you like, and those two cancel out. So I'm getting my derivative to be 2x divided times 4 divided by x squared plus 4 squared. Now what? Critical numbers. I need to know, where does my derivative equal 0? A fraction equals 0 if the top equals 0. And where is my derivative not exist? That's when the denominator equals 0. But in this case, the denominator can never equal 0. So I only have one critical number to worry about, and that is 0. There's the derivative, and there's f. If I pick a point to the left of 0, let's say -1, and I'm going to put that in there. If I put a -1 right there, that's -8 over a positive, which is a negative. And if I pick 1 and put it in there, 1 times 2 times 4, that's +8, divided by a positive, that's a positive. So I know negative derivative, the function is decreasing. Positive derivative, the function is increasing. F is decreasing from -infinity to 0, and f is increasing from 0 to infinity. And later on we're going to say, do you have a maximum or a minimum? This is a minimum, in case you're wondering. We're not there yet. And 40 is identical. I just need to take a derivative, and again, if I take a derivative of this, derivative of the top times the bottom, minus the top times derivative of the denominator, all over the denominator squared. I need to clean up the top. That is 2x plus 4 minus 2x minus 1 over x plus 2 squared. Those cancel out. My derivative is turned out to be 3 over x plus 2 squared. And now for my critical numbers. I need to check, where does this derivative equal 0? Where does this derivative not exist? A fraction equals 0 if the top equals 0. We know that cannot happen. A fraction does not exist if the denominator equals 0. That's when x equals -2. So I only got one critical number, and that is x equals -2. That's the only point I need to test. There's negative 2. There's my derivative. There's my function. A point to the left of negative 2, let's say negative 4. The top is always positive 3. The denominator, negative 4 plus 2 is negative 2. Squared, that's positive 4. Positive divided by a positive is a positive. My function is increasing. A point to the right of negative 2, let's say 0. The top is always positive 3. The bottom, 0 plus 2 is 2. Squared, that's a positive. So the function is still increasing. So f is increasing from negative infinity to negative 2, union with negative 2 to infinity. Something's happening at x equal negative 2. We'll figure that out in the sections to come. And the homework is listed right there. You're going to do almost identical problems that I did, except 53 has a small application. Just something to keep you interested. You know, something that math could make possible.